This video is going to cover inverse functions and how we can find these equations, as well as their domain and range. So let's say we had this function here. F of x is equal to 5x. So to find the inverse function, what we need to do is to invert or to swap the x and y values. So first we let y is equal to f of x, just to get our notation, and then we swap the x and y values. So we end up with x is equal to 5y. And then we just rearrange the equation to get y as our subject, which gets us y is equal to x on 5. And to complete our notation, we indicate this as our inverse function by saying f and then a little -1 at the top is equal to x on 5. What this visually looks like is if we have our original function y is equal to 5x, when we invert the function, we flip it across a particular line, and that is the equation y is equal to x, which in terms of inverse functions acts as a sort of mirror between these two functions. So our original function is y is equal to 5x, and then our inverse function is just flipped, and it looks like this. So that's what these inverse functions visually look like. Now let's take a look at the requirements for an inverse function, which is for a function to have an inverse, it must be a one-to-one function. In other words, this just means that for every one x value, there is only one unique y value, and vice versa. And although it can be difficult to just look at an equation and determine whether it's one-to-one or not, there is a rule that can help us out, which is the vertical and horizontal line test. And you can find more information about this in this video linked here. But to summarize, this method is where we draw a vertical line or horizontal line anywhere on our graph, and there should only be one intersection. If this is the case, then our function is one-to-one. So for example, for this parabola, we can see if we draw a vertical line anywhere, there will only be one intersection. However, if we draw a horizontal line, let's say at y is equal to 4, you can see that there are 2 points of intersection, meaning that this graph is not one-to-one. That is, until we do something with the domain. So what I mean by that is, if we look at this parabola here, it basically extends off to infinity. And what we can do is restrict the domain so it becomes a one-to-one function. And then it will have an inverse. And in terms of where we want to restrict it, well, since this graph failed the horizontal line test, we basically want to shorten the graph until when we draw any horizontal line, there is only one intersection. If I just start from the left-hand side, you can also start from the right-hand side, and we start shortening the graph, you can see that we keep going until you reach 0. Since x equals 0 is the turning point, now any horizontal line we draw only has one intersection. We can keep going and shortening the graph, but 0 is the smallest number we can pick in this case. Let's rewrite our function using function notation. So it's f, colon, and then we insert the domain. In this case, we've restricted the domain from 0, inclusive, all the way to infinity. So that's our domain. And this maps onto R, and then f of x is equal to x squared plus 1. Now, let's find the inverse function as well as the domain and range for where these functions exist. And I'll lay it out in the following steps. So first, like before, we're going to invert the x and y values. So swapping x and y, we get this expression, and then I'm going to make y the subject. So we end up with y is equal to plus minus root x minus 1. So you may have noticed we have a positive solution as well as a negative solution, because when we take the square root on both sides, we needed to consider both equations. However, only one of these works since we want a one-to-one function. To determine which one we pick, we need to use the domain and range. The domain of our original function was 0 to infinity, and a property of inverse functions is that the domain of our original function is equal to the range of our inverse function. Using this, moving on to step 3, if we look at both equations, one is y is equal to positive root x minus 1, and the other solution is y is equal to negative root x minus 1. And we know out of these potential inverse functions, only one exists, and that one must have a range of 0 to infinity, because we've specified that up here. In other words, since range refers to the y values, this means that the y values of our solution must be 0 or greater. And looking at our functions, the square root of any real number will be positive, and then if we tack a negative sign at the front, it makes this entire expression negative, which means that the range of this cannot be from 0 to infinity, so we can reject this solution. Now, we can write this in function notation, but we're just missing the domain of the inverse function. So to find the domain, we need to use this rule that the range of our original function is equal to the domain of the inverse function. So the range of our original function starts from 1 because that is our lowest y value, and it goes all the way to infinity. So our range is 1 to infinity. Since that's the range of our original function, that means the domain of our inverse function is also 1 to infinity. So the full function notation for our inverse function is this. And that's the process for finding inverse functions, including the domain and range.